Hi folks, it's Dr. P. The purpose of this video is to explain the 2's complement number system. Because binary numbers are constrained to having only two different values, 0 and 1, we have to find a way to represent signed numbers. Signed numbers means that each number has a sign, positive or negative. We can't use a plus or minus sign in our numbers, so we need to find another way to represent the sign of a number. What we need is a number system that, 1, enables us to distinguish between positive and negative values, and that 2, allows us to carry out binary arithmetic and get meaningful results. The way we satisfy our first criterion is to designate one of our bits as a sign bit. We'll use the leftmost bit to do this. Therefore, if I had a bunch of different signed binary numbers, all I would have to do is look at the leftmost bit, called the sign bit, to determine if the number is positive or negative. If the sign bit is 0, the number is positive. If the sign bit is 1, the number is negative. Criterion 2 is satisfied by a number system known as 2's complement. Let's dive into how we can get a 2's complement number. The first thing we need to establish is the number of bits we're working with. As explained in the video I made about overflow, our hardware is always going to have some type of limit to how wide our binary numbers are. In this class, we typically work with 4-bit numbers, which limits us to working with relatively small numbers. However, you may be working with a system that deals with 8-bit numbers, or maybe even 16-bit or 32-bit. But first, we need to understand what the limit is, and then we need to make sure that all of our numbers that we use have that many bits. No more and no less. The number of bits that we're working with sets a limit to the maximum and minimum values that we can express. That's also a limitation in unsigned numbers, but it's even more so a limit in signed numbers. So let's say that we're working with 4-bit numbers. All of the 4-bit binary numbers are written down here. You can see that only the numbers 1 through 7 have a 0 in the sign bit location. I'm kind of including 0 here, but 0 is a strange number, and then it's not really positive or negative. It's just 0. But anyway, 4-bit 2's complement can only express a maximum value of positive 7. The smallest number we can represent is negative 8. In 5-bit binary, only the numbers 1 through 15 have a 0 in the sign bit. So 5-bit 2's complement can only go from negative 16 to positive 15. There are similar limits for increasing number of bits, so we need to understand the constraints of our number system first. Converting a binary number to 2's complement therefore means that I need to start with a positive binary number that has the same bit width as whatever our system is. So let's consider the number 5 in base 10. We can represent this as a 4-bit number, a 5-bit number, and so on by putting more zeros to the left of the number. As mentioned, we can't represent 5 in base 10 as a 3-bit 2's complement number because there would be a 1 in the sign bit, which doesn't make any sense for a positive number. So 5 in base 10 just doesn't fit in a 3-bit number system. Positive numbers, once they're established in this format with the correct number of bits, are already in 2's complement. You're done! I call positive binary numbers universal because they work as unsigned and signed numbers equally, without any work on your part, other than to make sure that they fit within our bit width constraints. Making sure that your initial number has the correct number of bits is an extremely important first step that many students skip. I need to emphasize that your 2's complement value will very likely be wrong if you don't start with the correct number of bits. So now that we know how to generate a positive 2's complement number, how do we generate a negative 2's complement number? Well, we need to do 2 more steps. The next 2 steps are flip all of the bits, which means that all zeros become 1s and all 1s become zeros. Step 3 is to add 1. The result is a negative 2's complement number. So let's go back to our number 5 in base 10. To get the number negative 5 in base 10 as an 8-bit 2's complement number, we start by converting positive 5 in base 10 to an 8-bit binary number. That's step 1. Remember, we also need to make sure that 5 is going to fit in 8 bits. And it does. And we know that because positive 5 has a 0 in the sign bit. Step 2 is to flip all of the bits. All of the 1s become 0s, all of the 0s become 1s. Step 3 is to add 1. That's it, that's all there is to it. Remember, we can kind of smell check our result here. There's a 1 in the sign bit, which it should be because we expect a negative number. One weird thing about 2's complement is that our most negative number is going to have a larger magnitude than the most positive number. So in 4-bit 2's complement, the numbers I can express go from negative 8 to positive 7. So how do I generate that most negative number when I can't express it as a positive value in 2's complement? Well, the most negative number is always going to have a 1 in the sign bit and have zeros in all of the other bits. The most negative number is weird, but it's still valid. One last thing about 2's complement. Just as we know that with positive numbers, adding zeros to the left does not change the value of the number, only the number of bits, with negative numbers we can add 1s to the left and not change the value. So if I wanted to express negative 5 in base 10 as a 12-bit number, and I had already expressed it with 8 bits, then I just need to add 4 1s to the left. Okay folks, hopefully this video helped you to better understand how we express signed numbers in binary. Remember to keep practicing converting numbers until you feel comfortable with it. Until next time, stay well.